So I hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In our discussion today, we're going to look at the relationship between the ideal gas equation and the equation of state. And of course, this particular equation of state is the van der Waals equation, which is our topic of discussion for today. Now, in this case, from our last discussion, I mentioned that basically we can give the relationship between Boyle's law, Charles' law, and Avogadro's law using this particular relationship for pressure over nRT, basically giving us what we refer to as a compressibility factor. And in this case, we said that there are various ranges of this compressibility factor that we can consider. We just give it as a compressibility factor. And of course, we said that there's two specific cases we can consider for the concept of pressure and volume whenever we are trying to consider this specific factor. Now, I've given a graphical representation of this particular compressibility factor against pressure, whereby I said that this is a pressure in atmospheres against the compressibility factor, this specific scale. And then we said that for an ideal gas, the compressibility factor is basically 1.0 given as such. Now, there are various representations for a number of gases that we had given for the relationship between the compressibility factor and pressure. And of course, we had said that we can give a range of gases using this particular relationship, as we're going to see later. So in this case, I mentioned a few of the gases that I can give, for instance, ammonia, hydrogen, and oxygen. And this basically at the compressibility factor of 1.0. This one, of course, gave us the relationship of pressure, volume, and temperature of an ideal gas. And as we increase in temperature or the pressure, as we increase in pressure, of course, there's going to be some deviation from an ideal gas equation. And therefore, this one called for us to find a new way of trying to describe the real gases contrary to the ideal gas perspective from the ideal gas equation, of course, which is given in terms of this specific relationship. So therefore, this is going to culminate into the concept of van der Waals equation, which is basically an equation of a state that is going to give us the real picture of the behavior of gases at various temperatures and pressure. So therefore, in this case, I'm going to just mention this particular concept of an ideal gas, perhaps give an expression for this van der Waals equation, which is going to shed for us a light on how we can describe gases at perhaps low pressure and high temperatures, or at high temperatures and low pressure in this specific respect. So we said that the ideal gas equation can be given in terms of PV given as nRT. But if we try to consider this, I said basically we can have an equation of a state whereby we're going to have a pressure plus AN given in that specific case over the square of V. So I'm going to give a version of this specific equation, and then we're going to have this one multiplied with V minus NB. I'm going to explain what basically these particular variables or constants represent, and this is going to be nRT. So if you look at this is the ideal gas equation, and the next is an equation of state, which is basically the van der Waals equation as such. And we said that the difference between the ideal gas equation and the equation of state, like the van der Waals equation, this one is going to give us basically a clear picture of the behavior of real gases as contrary to the behavior of ideal gases, which we said basically that they are not going to be existent. But this one assists us to develop a relationship between different gases, considering the various aspects of pressure, temperature, and volume using that particular state. So basically, then therefore, I'm going to state what are some of the characteristics of this specific equation, which is going to be applicable for scientists and perhaps chemical engineers who work with gases at low temperatures and high pressure, of course, in order to find more accurate behavior of these particular gases. Now, therefore, the equation employs specific constants. Now, as we can see from this particular aspect of pressure, there's an addition aspect of n squared or v squared. And then at this particular case, for the volume, there's an addition of, there's a subtraction of NB, there's a subtraction of a particular constant N and B from this particular case. And therefore, I'm going to elaborate on why that specific modification has been done on this ideal gas equation from that particular case. So therefore, the equation uses a particular constants which I have said, which are going to make the equation experimentally, of course, viable in trying to, of course, have a relationship between experimental data obtained which deviates from the ideal gas equation. Now, the factor which has been added to pressure, which is AN squared over V squared, this basically is done in order to cater for the pressure observed for real gases at which is basically lower due to attractive forces between molecules. And that we had said from the kinetic molecular theory of gases. I've mentioned that one of the postulates of the kinetic molecular theory of gases is that there is no attractive forces between molecules or the molecules and the container, and therefore in the real sense these attractive forces are going to be experienced. Therefore, for us to cater for the this specific aspect of pressure which is lower that is observed due to attractive forces between molecules, we're going to add this specific factor in order to cater for that specific aspect of the ideal or the real gases as observed from experimental data. And then we're going to see that for volume, we're going to have an aspect of NB, which is subtracted from the volume. And this is done, of course, because of the volume observed for real gases are high due to the volume of the real gas molecules. And of course, we're going to have to subtract this specific factor in order to cater for that a specific difference in volume which is observed. And in this case, of course, the concept of A and B that we have employed are going to increase as the number of atoms increase. And of course, this is going to be, as we said, A is going to be a collection of pressure, which of course increases with the number of atoms, as we say. And the intermolecular attraction, of course, which is going to be also increasing the number of atoms, is going to be catered for by increasing or decreasing those specific factors, therefore, which have been expressed in the van der Waals equation. We're going to see that generally comparing the ideal gas equation and the van der Waals equation, the second equation is going to be more accurate in describing these specific samples of gases, and therefore it's going to be applicable in situations whereby we require some accurate data for scientists, as I said, and engineers working with the low pressures and high pressure, low temperatures and high pressure in that specific state. Now, we're also going to see that it's not this specific equation for the van der Waals equation is not as general as the ideal gas equation, and therefore this ideal gas equation of course assumes that gases are generally going to behave the same, but this is going to be applicable for individual gases, whereby we're going to see that for different gases the values of A and B are going to be different, and therefore this is going to be more realistic as compared to the general ideal gas equation. Now, in our subsequent discussions, we're going to give various values for the values of A and B, and from that one we can describe the various aspects of pressure, volume, and temperature using the van der Waals equation in various application areas. So check our description boxes for various links of other videos which are going to assist us comprehend this. And of course, I've discussed in some of the aspects of this ideal gas equation and the van der Waals in some of the videos, which I'm going to put a link in the description boxes below. So that is it for now, guys. Bye. God bless you. Catch us in our next video.